Okay, so hello after break. Okay, so today we start the second block of our lectures. So far we talk about programming, and these topics I mentioned so far covers subjects of laboratory classes in this semester. So during laboratory classes you will have programming in C, but also in second part of the semester, the standard template library. But in range of this lecture, there are two further parts. So the first part we start today is oriented on hardware. So I'd like you to know how computer works. So what are the technical aspects and what are the trends in hardware? So what's changing? From my perspective, very important is you to know or you to be able to distinguish between marketing and some ads we can find in on internet, like, okay, this processor is better than ever, and it's outstanding and so on. And I'd like you to be able to read technical documentation or specification and be able to decide whether in fact it is better and what are the purpose that it is better. So there will be several parts inside hardware block. So I'd like you to tell you about data storage, so hard drives. This lecture will be also connected with lecture which belongs to computer science tools, or so the second lecture, because I'd like in this lecture I'd like you to show you how we can handle with files, because I think it's more the matter of tool to read, write data in file than it belongs to information engineering itself. The second topic will be about interfaces, so USB, HDMI, and other interfaces. The third will be about processors, and probably there will be another lecture about computer graphics, also connected with computer science techniques, where I'd like to show you how we can use OpenGL library. At the end of January, we switch again to programming, and there will be about 3 or 4 lectures about object-oriented programming. So there will be introduction to object-oriented programming, which is topic for next semester laboratory classes. Okay, so that will be all for this for our program in this semester. In next semester there are no lectures, so so it will be the all knowledge I like to present you in this course. Okay, so let's start. So if you look at the if you look at the storage method, so we want to represent data. when your computer is running, of course, we use random access memory, so RAM memory. And random access memory feature is that it is very fast, so we can, transport data to and from the memory very fast. But the problem is that when you turn your power off, nothing will be preserved. So it is non-volatile memory. So what is the feature? So if you have random access memory, okay, it's not. It is not okay. So let's say so it is DRAM, so it's latency. So the latency of the which is related to the time we request data and we get data is 10 times bigger than in case of SRAM. What is SRAM? SRAM is even faster than DRAM. This memory is located next to processor, so next to core. So when you buy processor in specification, you can find that there is something like cache. Yeah, L1, L2, L3. So there are different levels of cache. They differ in latency too, but SRAM is the fastest memory in your computers. So assuming that the latency for SRAM is 1, you can see that for your RAM, so the RAM is 10 times bigger, but okay, it's for us, it's okay. Yeah, so we have now DDR4 or 5 or 6 in graphic cards, so it's work fast. But look, on the other side we have HDD, so hard drives, and the latency is 10 million times higher than comparing to RAM. So it's 1 million times bigger than latency of your random access memory. So there is a huge gap, yeah, between RAM and between HDD. So the solution now is to use solid state drives. They are faster than HDD, up to 100 times faster, but it's still, okay, 100, let's say even 1000, but okay, it's in, no, 100? Yeah, 100 times faster, but it depends on type of SSD. In the middle way, there is something which is called 3D X-Point, or what is the name of? Okay, I have to check it, but there is another solution which is used in server stations or server computers, which let us to store data permanently with lower latency. But this method is quite expensive. Optane, yeah, sure. So this method is still expensive. So you can see that there are some computers which with Optane, but in comparison, the capacity to price, this is quite it is quite high. I will tell something about Optane later on, but you can see that there is a huge difference between the way how data or bytes can be transferred in NAND, so in SSD and in Optane. Yeah? There is a huge difference. So you will see that for random access operation, the Optane works very fast. So what about size? For solid state drive, so for NAND drive, the size is even 10 times bigger than comparing to the RAM. So let's say the average size is 500 gigabytes up to 2 terabytes for solid state drive. In case of hard drive, okay, we can buy hard drives which are bigger than 6 terabytes, and the price is quite reasonable. So, yeah, so still for data storage, and I like to focus on data storage today, there are two options. And during this lecture, I'd like you to show how hard drives, solid state drives, how they works, and what are the differences, problems with maintenance, and what are the trends, and how we can, for example, how manufacturers boost or enhance their products. So let's start from hard drive. I think some of you may think that it is a little bit obsolete, but still in workstations and in servers, we have a lot of hard drives because, okay, we have bigger capacity compared to SSD. Okay, so here you have hard drives, hard disk assembly. So look, hard disk assembly or hard disk consists of plates which rotating with constant speed, and we have a head or actuated head which is able to read data from tracks located on the plater. Here we have a very strong permanent magnet, and it led to change position of the head. Here is the actuator axis, and this arm can be moved from and outside the platter, so it moves in this direction. So, and this is the way how every hard drive is built. Of course, to increase the hard drive capacity, several plates may be used, and from every side of the plate we have a head. So head is a tool which is used to read data from traces. So you can see that if you move arm in particular position, all arms on every plate are moved in the same position because they are fixed together. So they can't read or be positioned independently. So in this case, we are able to read and write data let's say, in parallel. So from every plate, every head reads data simultaneously. So some information about history. Of course, you don't need to remember this information. It's only to make your no, to give you some information and wider your perspective. So first hard drive was developed by IBM in 1956, and its capacity was less than 4 megabytes. Okay, it's not bits. It should be used capital B, megabytes. Its size was more than 2.5 cubic meters. Yeah. So and price was 15,000 bucks per megabyte. So look, from this point in history up to now, there was a great progress. Yeah. So now we have hard drives more than 6 terabytes. There are hard drives which are bigger than 10 terabytes now. Also, the size was decreased. The price per megabytes was decreased 150 million times. Yeah, so it's quite impressive. What is also was done, that average access time, so the time after which I get data, was decreased from 100 milliseconds to few milliseconds. So this is the progress which is made in computer hardware, not only in hard drives, but in processors and in other peripherals like interfaces. So we can observe that every 2 or 4 years, the performance is increased 2 times. So it's like a geometric progress. Yeah. Okay. So look, here you have a physical data structure. It is only to explain particular terms here. So every plate, on every plate, we have something which is called a track. So tracks. So they are circular path around the with a fixed radius. So on hard drive we can have, you know, a dozen of tracks. But if we have many heads and they are fixed, so they can be positioned only, you know, together. When we take all tracks for particular head position, we get something which is called a cylinder. Yeah, so cylinder is a cross section. So cylinder contains all tracks which can be read for in particular head position. What else? The track is divided into sectors. So sector is the smallest amount of data which can be read from hard drive. In older hard drives, it's not true now, in older hard drives, there was a geometrical sector. So every track was splitted into the same number of sectors. So if you can see that this radial lines, and every the area between these lines corresponds to a sector. So here the sector starts in this point and finishes in this point. But you can see that because sector consists of, let's say, 512 bytes, now all sectors are about 4 kilobytes. So the sector capacity is the same, but you can see that if this sector is located next to rotation axis, the data has to be, the density of data is higher than density of data on the circumference. Yeah. So, so what was done? Okay, the geometrical sector was replaced by sector. So this, so on tracks which are next to rotation axis, there is less sectors than on the outer tracks, but the data density is constant. So we can store data with the same density. So how hard drives read and write data? On the platter, there is a specific material which is magnetic sensitive, and if you want to write 0 or 1, the head will switch domains. So the orientation of the magnetic domain on the surface correspond to 0 or 1. So let's assume that this orientation is 0 and this orientation is 1. So we have 0, 1, 0, 1, 1, 0, 1, 1. Yeah. So we are able, or the head is able to change the orientation of this domain. So there are two standards. So longitudinal recording. In this case, domains are flat. So they are located horizontally, but we can have also perpendicular recording. So in this case, domains are vertical. But the problem is that we can, of course, we can increase domain density because we are able to, in certain area or range, we are able to fit more bits. But the problem is that the reading head is larger than size of the domain. Here, okay, the size of the head is enough to affect only on a single domain. Here, not. So it was solved using a head which consists of two poles. The one pole is very sharp, and the second pole is wider. So the magnetic stream density here is lower than the switching threshold, so it doesn't affect the domain here. But here the density is very, it's higher. So only this domain will be affected. It is a problem with density, because if we want to increase the hard drive size, we should increase the density, or we should increase the number of platters. or we should increase the size of hard drive platters. You can see that hard drives of size 2 and 5 inches, they have lower capacities than the 3 inches hard drives. Yeah, so this is due to the limitation in writing density. Last year, I think Western Digital announced that they used a new, or tried to develop a new head which use I think microwaves to initially to change the domain orientation. So there is still a magnetic reading and writing head, but when there is a huge density, to reorient particular domain will require additional energy, and this energy is supplied by a microwave source. Yeah, but okay, I don't know whether these hard drives are were introduced to market, but they announced that they will be able to produce hard drives up to 40 terabytes. Okay, so this is, general scheme how hard drives is built and how it works. From my perspective, the most important is you to be able to distinguish how this physical limitation, how they affect on the parameters which are presented in specification. So there are several crucial parameters of hard drives you should know, and you should understand why they are so large or small, and what is better. Okay, the first is access time. So it is average latency between data which was request and the time the hard drive start to transfer this data. So look, there are several factors which affects the access time. First, if I request particular data, the first thing the control system has to do is to position the head over particular track. So this is called a seek time. So seek time is the time of transition of the arm from current position to desired position. So it takes 3 to 15 milliseconds. So we have to spend this time to move head from this point to outside part. The second parameter is rotation latency, because even we set our head over track and we want to, for example, read sector 14, but we are here, we have to wait until this sector will be over, will be under the head. So it is called a rotation latency, and rotation latency depends on the rotation speed. So what is the standard rotation speed for current hard drives you can buy. Yeah, so 5 RPM or 7,000 RPM. That's are the speeds for custom hard drives. So, but in servers, we can find faster. So the hard drives of speed 10,000 or even 15,000 rotation per minute. So you can see that it affects the rotation latency. So if you want to buy a hard drive for, let's say, for NAS, so to store your photos, what is better, to buy the hard drive of speed 5,000 RPM or 7,000 RPM? Yeah, so for data storage, it's not so important. But if it's your, only drive in your computer, of course, it's better to have the hard drive of higher higher speed. But you should be conscious that there is the rotation speed is not so okay, it is important, but sometimes if you have, for example, hard drive of with 7,000 RPM and data density is low, it can be even slower than hard drive of 5,000 RPM. Of course, rotation latency will be higher, yeah, but the transfer rate may be higher for the slower one. Yeah? It depends also on the data density. So next to hard drive, so there is a hard drive controller, and there is something which is called a cache. So every hard drive has, in specification, you can find the cache size. So now I'd like to tell you something about cache. So what is the average size of cache in hard drive? Yeah, there are hard drives. Yeah, let's say that is average. Budget hard drives have about 20 or 30 megabytes. Most hard drives have 64 megabytes. There are also hard drives with higher, larger cache. But what is going on in cache? Look, if I requested to read sector 14, is very probably that in the moment I will request the sector 15 and 16 and the other sectors on the track. Because my reading head is located over track, all data can be read and they are transferred into cache. So if after some time, the PC computer will request to read the next sector and it is located in cache, it can be send immediately. So without latency time, without rotation latency, and without seeking time. Yeah. So because it is in a cache, there are no latency. So it is sent with a speed of interface which connects PC with hard drive. So usually when we read clusters of data, so not only a single sector, but sectors which are located on the same track, we can improve the hard drive performance. But what do you think when we want to transfer, let's say, a read file of size 1 gigabyte? Does cache size affects the hard drive performance or the transfer rate or not? So, for example, I have a game which I'd like to run, and in the initial phase about 1 gigabyte of data has to be read from hard drive. They are located next to each other. So let's say they occupies the traces in some region. And does the cache size affects the performance of this process?
Not really.
Yeah, so why?
Because the data amount we need is much higher than the cache size we have.
Yeah, that's true. So if amount of data is bigger than cache size, there are no improvement. Yeah. So cache size plays a role when you read small files, yeah, or you write small files. Because, for example, if I'd like to save data, this data are stored in cache, and then they are transferred to hard drive on a speed which hard drive can perform it. Yeah. So if we have the file which is smaller than cache size, we can transfer it, very fast. From perspective of computer, of course, they will be right on hard drive a little bit later. Yeah. But if you want to, for example, write a 1 terabyte file, it doesn't matter whether you have 32 megabytes or 64 megabytes. It doesn't matter. The transfer rate will be limited by the hard drive performance. Otherwise, if the file is smaller, it will be transferred to cache with speed, which is limited by interface throughput. And interface throughput is several times higher than the hard drive performance. So look, the average transfer speed to buffer, so to cache, is about 120, transfer speed to hard drive is about 128 megabytes per second, while by interface it's about 600 megabytes per second. So if you have cache, you can transfer data with this speed. If the file is bigger, the transfer rate will be like this. So if we take SSD, of course, it is faster, so it can utilize the full speed of serial ATA or NVMe or other interface it used. But now I'd like to tell you something about durability of the hard drive. So what are the factors which affect or maybe may generate a hard drive failures? So what do you think? Yeah, physical impacts. What does it mean, physical impacts? Yeah, so look, because we have head, this head doesn't is not so there is a thin air gap between head and platter surface. Because platter is running, yeah, so it's rotating all the time, there is generated a thin air pillow and there is a gap. So the head doesn't touch the surface, but due to physical impact, so when it's vibrations or our hard drive drop down, it may happen that the head will hit the platter surface, and in this case it will destroy the head and it will make no, it can destroy the surface of the hard drive. So due to this process, we can observe that something which is called a bad sector will be generated. So we will be not able to read data from this region, but if this process will be repeated, you can there is a risk that the hard drive will be corrupted. But there are some methods which let us to, or let hard drive to protect against such events. So first, when you power off your hard drive, the head is parked, so it is moved outside the platter surface. So automatically, when the hard power is when the hard drive is powered off, this arm is moved in this place, so to the parking, yeah. And when the hard drive, which is not supplied, for example, fall down, nothing will happen in most cases. So, for example, if you have your computer and it is, turned off and it collapses, yeah, nothing should happen, because, okay, you can try. But most hard drives has also accelerometer, which is embedded. Okay, which is embedded into the controller, or some computers has accelerometers embedded into control system. So if the accelerometer will detect a free fall, so it detects that your computer or hard drive is falling down, it power off. So in this case, the arm is parked, and when it hit the ground, nothing should happen. But okay, don't try it. Okay, but there is a protection against it. The more problematic are vibration. So, for example, we work in a condition where somebody is drilling something, yeah, and it may generate head vibration, and the head may hit surface. So, vibration is the most prominent factor which may generate problems or hardware failure. The second factor is, so look, I don't know whether you think about it, but hard drives has metal cases. Yeah. Even, they are manufactured in China, still they have metal cases, yeah, not plastic. Why?
Maybe to protect it the best possible against magnetic radiation.
Yeah, of course. So the metal case creates something which is called a Faraday cage, yeah? Because we store data in, as a magnetic domains. The external interference from, let's say, storm or another sources of magnetic or electromagnetic interference, it may happen. The reorientation, domains reorientation. So if you have Faraday cage, so you have metal case and the platers are surrounded by metal cage without any gaps or holes, it is protected. Yeah, so you should know it from physics. Yeah, so therefore even Chinese hard drives have still metal case. Okay, yeah, there is a question that it is possible for hard drive to lose data over time, where it's lying unpowered for years. So for hard drive, there are no difference whether it is powered or unpowered. Yeah. It is very important for example, for solid state drives, because they can lose data even faster. The As far as I know, the durability of hard drives, so the way how the data are, organized, is higher than 100 years. So in theory, of course, in theory, nothing should be, if you have a hard drive which is protected by a metal case, nothing should happen for years. Yeah, but yeah, so comparing to solid state disk, the data durability is higher. The highest durability is for magnetic tapes. So if you have magnetic tape, it is even long lasting than hard drives. But there is another problem. Yeah, maybe it's a little bit philosophical what I told you, but look, even we are able to store data for 100 years on hard drive, I think after 10 years we will not be able to read this data because there are no computer with, let's say, such interface which let us to connect this hard drive. Yeah. So, So let's say that 10 years or maybe 20 years is enough, yeah, because after that time the hardware progress will be so huge that it, it will not be possible to read this data. I don't know whether you remember times where data were stored on flexible drives. So let's say we have a lot of disks, small disks, and we had a reader. Okay, I still have computer with such drive, but uh, it's hard to read this data now. Even yeah, even it's yeah. So now you can think that after 5 or 10 years, the hard drives with serial ATA interfaces will not be used in computers. Yeah. Okay, so let's switch. Let's switch to. Uh, okay, yeah. So maybe I mention something about addressing because on hard drives, when I told you about memory, in computer memory, so in RAM, we are able to address every byte separately. On computers, we are able to address we are able to address only a sector. So we can to read so we can read only a single sector. So this is the smallest amount of data which can be read and addressed. In the on the side of the hard drives, to read particular sector, several values has to be defined. So number of cylinders, so the cylinder, the head, and the sector. Yeah, but in fact, for all hard drives, SSDs, flash drives, and other storages, we use not cylinder head sector addressing, but we use logical block addressing. So logical block addressing is 48 bits address. So we are able to address 2 to power 48. So if we have sector of size 4 kilobytes, we are able to address 1 exabyte of data. So it's enough for some time. So and the hard drive controller will convert LBA to CHS standard. So this is typical. So we can use this addressing for all of drives, not only hard drive. Yeah. So now I'd like to tell you something about SSD, so solid state disk, because they are now in consumer computers. They are much more popular and they are cheaper and cheaper. Yeah. So in fact, there are two kinds of hard drives. The most popular are NAND flash. And the other is DRAM. So we have DRAM memory, so very fast memory, and we have additional backup. So this drive consists of two elements. So memory, volatile memory, and hard drive. So when the hard drive is powered off, data are transferred from hard drive to DRAM, and when it is powered off, it has independent supply, data are transferred from DRAM to hard drive again. So it costs a lot, yeah, because it's in fact it has a lot of RAM memory and additional hard drive, so it can be used for very specific applications. So for us, the most interesting is NAND flash. So look, what is typical? When we have NAND flash, the reading speed of a single sector is 25 microseconds and writing is 250 microseconds. So let's try to analyze or calculate what is the performance. So if I am able to write 4 kilobytes, let's say for 4 kilobytes times, oh, okay, divided by 0, 0, 0, 0, so it's milliseconds, 25. So this is the amount of time in which I am able to read 4 kilobytes. So look, in theory, I am able to read 160 megabytes per second. Let's go to this example. So look, the hard drive is able to read write 128 megabytes per second. So it seems that the difference is not so so huge. Yeah. Look, if I'd like to write data, I am able to write only 16 megabytes per second. So it's even slower than hard drives. So why the solid state hard drives performance is definitely better than the performance of the hard drives, so HHDs. Because if you connect the average SSD, you can get, let's say, more than 500 megabytes in read and write. If you use NVMe or M2 interface, you can read data with 4 gigabytes or 2 gigabytes. So now I'd like to explain you, maybe not now, but in a moment, I'd like to explain you why having SSD, we are limited only by the throughput of interface. Even the speed of writing and reading data from a single cell is comparable to a hard drive. Okay? But before we do it, I'd like to show you how NAND memory works. So look, here we have a single cell which is able to store 0 or 1. So this cell is built as a transistor. So how transistor works? Oops, I have problem. Still, I have problem with my laptop. So hope some of you know what the transistor is. So transistor is a basic element which is used in computers, but in fact it behaves like a switch. So let's say that here I have in. Yeah, I know that it's bipolar transistor, not TTL, but bipolar transistor. Here we have MOSFET transistor. The symbol is different, but from my perspective, the most important is you to know how it works. Yeah, you have electronics and electrotechnics, so there you will be able to distinguish between bipolar transistor. So this is the symbol of bipolar transistor, and MOSFET transistor. So I have in and I have out. So here I can have source, something which is called source. Here I can have something which is called drain, and here I can have something which is called gate. And here I have source, and here I have drain, and here I have gate. So what's happened if you put voltage to gate, the switch is closed. So the current may flow from source to drain. So it works like a switch. But if the gate voltage will be below the threshold, this switch will be opened, so it will not be closed. Okay. So it happened when I have standard transistor. So I have drain, source, and here I have gate, and the voltage is here. But here you can see that there is something which is called floating gate. So floating gate is the element which is not directly connected to gate and is not directly connected to this part. Okay, but I can charge or decharge this gate, because if I put a high voltage here, this gate will be charged. So the current will be induced here and it will be kept, because it is not, it is isolated from other parts. This current will be stored here for some time. Yeah. So in this case, when the floating gate is charged, it's enough to put here voltage which is below threshold, because this potential and this potential sum up, and in this case, the transistor will conduct. If the voltage is discharged and you put here under threshold voltage, this transistor will be closed, so it will not conduct. So when I'd like to write 1 to NAND, I have to charge this gate. And then when I'd like to read whether here is 0 or 1, it's enough to supply under voltage potential and verify whether this transistor conducts or not. Okay. So in fact here we have capacitor, because here we have potential and here something is induced. So most of you have capacitor, So how capacitor works on, I think, in secondary school program, or maybe even during this study. But the problem with capacitor is that there is a current leakage. So after some time, this current disappeared. So in this case, it makes the it may happen that we lost our data. Okay. So therefore, when you read documentation of your hard drives, there is written that you should supply your hard drive once per week, for example, at least. No? What is the durability of this capacitor? Okay, it depends on manufacturer, but it should be years, yeah, not weeks, but years. But there is also mentioned that you should supply your hard drive, at least every week. So durability of this maybe not hard drive, because durability of solid state disk is high, but data durability is lower compared to hard drives. So rather, it's not good option to use solid state disk to have a backup of data you keep in your somewhere, yeah, outside. So don't do it. So I don't know whether it's 100 years, because it is it was declared in specification, but at the same time they declared that it should be supplied every 7 days. Yeah, so so it makes some problems, but it depends, of course, on the environmental aspects. So look, what do you think? What are the factors which can affect or may improve or decrease the durability? Of course, temperature. If the temperature is high, probably, or low also, but it's outside the normal temperature, it may speed up the current leakage process. The second factor is humidity. Yeah, okay. We will be talking about different types of cells, but in fact, they are, from this perspective, there are only a little difference between them. So remember that environmental factors are very very important for solid state disk durability. Okay, so now several information about different types of memory cells. So in SSD, beside the environmental factors, the SSD durability is limited by number of write cycles. So look, depending on the solid state drive you have, the number of read cycles is limited. So there are solid state drive SSDs consisted of single level cell, and every cell can be written 100,000 times. MLC. So in hard drives you can buy in standard shops. You don't have hard solid state drives like this. In fact, we can use MLC or TLC or QLC. So look, if you buy the cheapest hard drive, solid state drive, they are TLC or QLC, so triple level cells. So in a single cell, we can encode 3 bits, sorry. And look, the number of the number of write cycles is limited to 1,000 cycles. For MLC, 3,000 cycles. It means that if you have solid state drive, you can write every cell 1,000 times or 3,000 times, or for QLC even lower. So if you buy your hard drive and you see, okay, variant is 5 years, in documentation you can find that it is limited to, let's say, 5 petabytes of data, which can be right there, yeah. So so it's not only the time, but also like in car, yeah, the distance or the amount of data which will be right there. So how hard drives reduce the problems with this? Because, okay, you can imagine that we can write particular cell more than 1,000 times. Yeah? If we have cache, for example, and we download and upload some elements, yeah, the particular cell may be written more than 1,000 times. And in solid state drives, there is a cell routing. So the address of the sector or address of the cell can be dynamically changed. So solid state drive controller tries to balance the number of write cycle for every cell. So it can reroute address of sector, and it can attach this address to another, part to keep all elements balanced. But there is a problem if you have solid state drive and it is almost fully used. So you don't have empty space on this hard drive. So let's say we have 100 or 1 gigabyte of memory. And in this case, the routing is very limited. Yeah? So if you write and read new data in this area, it may happen that your hard drive fails even sooner. So remember that if you have solid state drive, you should have, okay, at least 30% of free space all the time. So therefore solid state okay. But does the audio was broken now, or it was like this all the time? Okay, I don't know. Probably there is something bad with internet connection. Okay, so look, the application of solid state drives for in systems where there is a huge retention of data, so we write a lot of data, we delete them. So for this application, it's better to use hard drives. Or to have a solid state drive, which is bigger or 2 times bigger than amount of data we need. Okay. Okay, so now I'd like to tell you something about another, I think, very vital parameter, which is specified for all for all drives. So there is input output per second. So mostly, or most manufacturers is focused on the throughput. So but the IOPS is also very important. So let's assume that we want to request several distinct elements from our storage. So for example, I'd like to read 75 or 100 files, yeah, at a single, maybe not request, in subsequent requests. So for hard drive, I can perform 75 to 100 IOPS. For server hard drives, I can do it. I can generate more IOPS. So for SSD, I can do 400 to 8,000 IOPS. For SSD using NVMe interface, so PCI Express, let's say, I can perform 100,000, 160,000 IOPS. But there is a little thing, Q of size 32, and I have Optane. So for Optane, I have performed 170,000 IOPS, but the queue size is 3. So now I'd like to tell you what is the difference and why we, having SSD, we are able to perform most operations faster compared to HDD, even the time of reading data from particular cell is comparable. So the most important thing is that for SSD, we can do this elements in parallel. So we can have several channels which are used to read and write data. For hard drive, okay, we have single head or single arm. So we can do it only, we can process only a single request in particular time. So here we can make it in parallel. But there is another element which makes SSD faster. We have queue. So if there are several requests, the controller can reorder them in a way which optimize the process. So sometimes the request which arrived after can be processed earlier, yeah, because the controller allocates allocates the request to particular part of memory. But in fact, you can see that if we have not so many requests per second, the performance of SSD is decreasing because, for example, if we have 2 requests, the performance is less than 20%. But if we have 32 requests or 30 requests, the performance of SSD grows. So if we have Intel Optane, the memory access to memory cell is faster. So even we have queue of size 3, so we don't have, a parallel channels, we can get this data very fast. So for random access requests using Optane will be faster, but Optane is used for cache, not for permanent data storage. It is used for storing files which are used very often. So if the difference between SSD in SATA serial ATA and SSD in the NVMe interface relies on the number of parallel channels we can allocate and using which we can read and write data. So therefore, we can create SSD, which is capable of transferring data 600 megabits per second and 600 megabytes per second and 2 terabytes or gigabytes per second. Yeah, so it's up to, it depends on the number of independent channel we can use. But remember that there is something behind the scene. So there is a queue in which we can reorganize packages. So the amount of time which is used to deliver a single package, if only a single request is generated, is comparable to hard drive. Okay. So now I should tell you how we can use several hard drives to improve the overall system performance or to increase the system's security. But I think we have 5 minutes, so it's not enough time to do it. So I do it next week. And next week, I will also show you how we can read, write data from hard drive, from disk, from files in C++. So that's all for today. Thank you for your attention and goodbye.